This is the first lecture that we have on our chapter 2 regarding the descriptions of light in our course on optics. So in 2.1, titled Electromagnetic Waves, we will briefly go through the very first notions of electromagnetic waves. After that, I will bravely start by introducing to you the Maxwell's equations in vacuum. And don't be spooked, they look very intimidating at first, but we will be going through them quite a few times during the course. And in the end, they are not the main thing to understand in our course. It's basically just the Maxwell's equations that provide us a tools to formulate a wave equation, and from that, we really do not necessarily need to focus that much on those pieces of equations, but rather we can deal with the wave equation. That might be an easier concept for a starting student to grasp. So once we have introduced to you the Maxwell's equations in a microscopic medium, meaning in vacuum, we will introduce to you the wave equation very shortly. We do not yet derive it from the Maxwell's equations. We do that later on in the course. And once we know the wave equation, how that looks like, we can find a solution for the wave equation. And of course, that piece of mathematics tells us what is a wave from a mathematical point of view. And then once we have that, we have a function describing a propagating wave, a propagating piece of light. Then we can start looking into the properties of this wave. So we can, for example, solve the function and realize that we can have solutions for the wave equation. It's a differential equation, of course, that are so-called time harmonic waves. So we will be showing you the math, simple sinusoidal functions, and describing what it implies in terms of the properties of light. We will be speaking a little bit about the spatial evolution of time harmonic waves. So with the spatial evolution, I just mean that how it propagates, how a wave propagates forward, and how the piece of mathematics then evolves accordingly. And then I will introduce, related to this propagation, the k, which is the wave vector of the wave. Basically, when we generalize our description of a wave into a three-dimensional space, then k, the wave vector, actually has a better meaning since it really becomes a vectorial quantity. And then that vectorial quantity, the wave vector k, tells us in which direction in the 3D space our wave is propagating. Then we will speak about the time dependence of the time harmonic field, time harmonic wave, and we will show that the time harmonic wave, as the name already suggests, is also periodic with respect to time. And we will introduce to you the concept of angular frequency, which is quite often used as a parameter describing the angular the temporal oscillation of a wave. And then once we have introduced the basic bits of mathematics that give us a description of a wave, then we will look into the consequences this makes into light and phenomena that are related to propagation and interaction of light with matter. And the consequences of the wave nature of light basically are the interference effects and the diffraction effects that we will be focusing on laterwards in this chapter. But we want to introduce these main notions to you already so that you roughly know what you will be facing on the later parts of the course. And then finally, we will close down this lecture by speaking a few words regarding the different wavelength regimes. So basically, I will be saying something that comes to mind regarding visible light and ultraviolet radiation regime, and then the slightly longer wavelength regimes of having near infrared wavelengths. So this is what we will be covering in this lecture. So very basics and nothing less, nothing more. So let's start with the basics using the little bit cheesy font here. Light is, of course, electromagnetic radiation, as we all know. And what this means from the historical point of view, of course, is that the Maxwell's equations that were originally found by Clerk Maxwell in 1865 basically tells us how and what is how light propagates, how it interacts with matter, and what it is. So, and Maxwell did not come up with all the equations. So basically what he mostly just did is that he compiled together the already existing laws governing magnetism and electricity. And this gave rise in a possibility of actually having electromagnetic interaction. And before Maxwell, it was not yet clear that the electricity and magnetic effects, they were actually related to each other. And how this happened was that the Maxwell made a slight addition into the existing equations, and that gave rise to the possibility of actually forming a wave equation out of Maxwell's equations, and that was the kind of huge revelation at the time. So, Maxwell equations that we'll be introducing to you shortly, and in addition the Lorentz law, and incidentally this Lorentz law was part of the original Maxwell's equations. They perfectly describe the phenomena of electromagnetic interactions. So that's all in essence what we need to understand what happens when light hits a matter, and that's it, and how light can propagate in the first place in different media. And the good thing and the interesting thing for us from this this course point of view is that when we start from Maxwell's equations, we can now use them, compile them together to form a wave equation. And then once we solve the wave equation, we have functions that describe propagating electromagnetic waves or disturbances, pulses of light, for example. So what that means in other words is that we will have a mathematical treatment for light, and this is of course nice for engineers, because once we have mathematics to describe something, a process, then we can actually quite quantitatively understand the process, and we can even predict what will happen in different scenarios of interactions. So this is of course most of the time a starting point for engineers and physicists. We want to form a mathematical treatment for our phenomena, processes, so that then we can actually quantitatively understand what happens. And this motivates us, of course, to introduce to you briefly the Maxwell's equations in vacuum. So these are the so-called microscopic Maxwell's equations. So this means that we don't really have macroscopic quantities such as refractive indices yet in here. So basically we are just not thinking of bulk materials, but rather just like a lone electrons in vacuum. And then between electrons we have light, electromagnetic radiation propagating here and there. And the Maxwell's equations in this concept, in this setting, like we usually use differential form to describe these equations. And in all simplicity, they are of this form. So we have four equations. The first one, we have the divergence of the electric field. So that nabla dot there is the dot product. And the nabla there, of course, gives us the divergence. And E is the electric field. And the divergence equals to rho divided with the permittivity in vacuum. So epsilon naught is the vacuum permittivity. And the rho there is the electric charge density. So essentially electrons and their density. This is the first Maxwell's equation. The second Maxwell's equations looks very similar. The left-hand side of the equation. So we take the divergence of a magnetic field, and then we know that this is equals to 0. So that this is the Gauss's law for magnetism. The first law there, the divergence for the electric field, that's the Gauss's law. So this basically tells us that always the divergence of the magnetic field is 0, and this is often used in when we are like making, for example, wave equations out of Maxwell's equations and doing other bits of derivation. In other words of saying, maybe one step back, this divergence of B means that there's no kind of sources, no magnetic monopoles exist that would give rise to a static magnetic fields. So that's the kind of thing that we have here. So like we may have electrons that are just staying still, and those electrons give rise to static electric fields. So if we would not have propagating electromagnetic radiation, but rather static fields, then just the location, like not non-moving electrons and their density, so the electric charge density, that gives rise to a static electric field. but no such things exist when we are like looking at the magnetic field. So the like stationary electrons, they do not give rise to static magnetic fields, but rather we should have currents of electrons that would give rise to static magnetic fields. So the third Maxwell's equation, now let's move forward. We will calculate the curl of the electric field, and we know that that must be equal to the minus time derivative of the magnetic field. So this is a little bit strange looking equation, I guess, to begin with, but this is something that kind of connects together the electric field component and the magnetic field component of the electromagnetic field. And this equation 3 is known by the name of Maxwell-Faraday equation. And then we have the final equation, number 4, which is the Ampere's circular law. So we are calculating the curl of a magnetic field, and then this is equal to the mu naught vacuum permeability times J, and J is the electric current density. So essentially moving electrons now as a source term of giving rise to electromagnetic fields. And then we have a term of vacuum permeability mu naught times the vacuum permittivity epsilon naught times the time derivative of the electric field. And this is the fourth equation known as the Ampere's circular law with Maxwell's corrections. So essentially Maxwell added this electric field spatial derivative in here, this term, so that we actually have a full picture that gives rise to electromagnetic radiation. So before, there was a law of Ampere's circular law that was known. So essentially, for example, a moving current, J, would have given rise to a static magnetic field, and vice versa. If we had a static magnetic field, we saw that gave rise to a kind of a static current. But here, like Maxwell added this term, that actually then gives rise to a possibility of having electromagnetic radiation. So these are the names of the terms. I already discovered them, what they are, so that you already know them. And then the equations, like I mentioned, the first one is known as the Gauss's law. The second one, the divergence for the B field, is known as the Gauss's law for magnetism. Then the law 3 is Maxwell-Faraday equation. So that's the divergence. Curl of E equals to the minus time derivative of magnetic field. And then the equation 4 is the Ampere's circular law with the Maxwell's correction term. So this is, in all its glory, the Maxwell's equations in vacuum. And this is starting point on our course. It looks awful, but just give it a time. We will stumble upon these equations quite a few times during the course. And maybe, hopefully, at the end of the course, you actually are having a lot more understanding of them, what they physically may mean. And if you don't worry. The focus on this course is not really on the Maxwell's equations, but rather on their implications, so on the wave equation and the related math. And in the related math, basically, we're mostly dealing with the sinusoidal functions, so that the level of mathematics is, in the end, not overly complicated in this course. Now, like I promised already, the Maxwell's equations that we have shown to you, they can be compiled together, and using that, we can derive a wave equation. And in a nutshell, the wave equation is in a form. We will derive this later to show that what actually happens and what it means. But we calculate the second nabla on the electric field, and this is equal to the vacuum permittivity epsilon naught times the vacuum permeability times the second partial derivative of the electric field. So this is the wave equation in three-dimensional case and for a vector field. So the electric field is a vector field, and then basically this is a differential equation. On the left-hand side, we have spatial derivatives, and on the right-hand side, we have temporal time derivatives. And if we solve a field that or find a field that is a solution to this differential equation, then we know that this solution describes a propagating electromagnetic wave or electromagnetic disturbance. And of course, similar wave equations do exist for the B field, for the magnetic field contribution, for the electromagnetic field, so that they don't worry about that. But more on that later. Now we just need to focus on electric fields or the electric field component, and that's enough for our description right now. The simplest solution that can be imagined and found is basically the case when we assume that the electric field is time harmonic with respect to the temporal evolution. So if we take a wave psi, and in the simplest case, we have just a single coordinate z that tells us a spatial dependence. It's just propagating in one direction, the wave, and then it has some kind of time dependence. The simplest form that we can imagine is that we have some constant amplitude for the wave, telling of how strong the field is, how much energy it is transferring from point A to point B, and then when you have sinusoidal modulation, that depends on the spatial location, the z coordinate, and it depends on the time. And then we have this kind of wave vector here, k here. I will be introducing to you later how that gets defined. And then we have the v there, which is the speed of light. So in the simplest form, this is a time harmonic wave, and this is the math that we will be starting to deal with and looking into the details. So basically, it's a function of two variables, z and t, and once we would know the speed of light, and once we would know the amplitude of the wave vector k, then we would be, and the amplitude of the wave, we would be entirely knowing how the wave would propagate in our system of interest. So A is the field amplitude, K is the wave vector. Of course, right now in this description, the wave vector is still a scalar valued quantity, but in the future that generalizes into a proper three-dimensional vector. So that's why I'm still calling it a wave vector here, not a wave scalar. And then v is the velocity of the wave. Most of the time it's the c naught, so the speed of light in vacuum. And then this sinusoidal modulation describes how the phase of the wave evolves when we are either letting the time flow, t flow, or we are looking at the wave in different spatial locations, so in different locations of z. This time harmonic field, and essentially time harmonic field just means that it oscillates this kind of sinusoidally with respect to time. Another way of looking at it is that if it just oscillates sinusoidally, we only have a single frequency that describes how light looks like. So in other words of saying, time harmonic field means that then our field is also monochromatic. So essentially, as the meaning of this term means, consists of only a single color, monochromatic. So that's good piece of information for you to memorize. What is the meaning of a time harmonic field, and vice versa, what is the meaning of a monochromatic field? So when I'm, for example, in an exercises, I'm asking or I'm describing the problem that we have a monochromatic field, then that essentially just means that we have a time harmonic field, and essentially that just means that the time dependence of the field looks like this. So we can just describe temporal dependence using a simple sinusoidal function. Let's get forward. So let's now try to derive the main properties. So essentially, like, what is a wavelength? What is the physical meaning of the wavelength of a light? And what is the wave vector? How does it look like? And what is the amplitude of the wave vector? So let's just lock down our coordinate system such that we just now look at the wave at an instant of time t equals 0. And since we have a harmonic function, now it only depends on the coordinate z. So they mathematically put this physically corresponds to or mathematically corresponds to the case that we have the psi, the wave solution, the wave function, and then that only depends on the coordinate z. So we have still the amplitude of the field A, and now we are modulating the psi. And since t equals 0, only thing that is left inside the argument of the sign is that we have the k, the wave vector, times z. And we can now easily plot this, and as you can see on the figure, it looks exactly like a sine. And interestingly for us, we now see that this wave reproduces itself after a distance of z equals lambda has passed. So as we all know, sines and cosines, they are periodic functions. So after a while, they repeat itself. And this gives us a tool to define the wavelength lambda as a property of the wave. So essentially, the wavelength is defined by this kind of physical notion. So after a while, the wave reproduces itself, and this distance, the shortest distance that we can imagine after which the wave reproduces itself, that's known as the wavelength of light. So let's repeat what that means mathematically is that we can start from 0. That equals to the a times the sine of 0. And using our notation, we have the psi describing our wave. So at the location of z equals 0, the value of the function is 0. And then now we go to a one distance of wavelength further forward. We see that now we have a function of a form a times sine of k times z, and this should be 0, as we know from the equality. And this, of course, implies that whatever we have inside the argument of sine, so what we ever have here, like this has to have of a given form, since we must have 0 in the end. And of course, we must have 0 for all the amplitudes that we can imagine, so that this then implies to us that the k times lambda, of course, after the propagation of z equals lambda, this must be equal to 2 pi of m, where m is an integer, so that we have still a 0 equality. So m is an integer, and now we just take the smallest possible wavelength we can imagine. So we take m equals 1 case, and using this we can now define what is the amplitude of the wave vector. And this can be solved to be the case that we solve this equation with respect to the k, the amplitude of the wave vector, by just placing m equals 1 in here. And this simply gives us that the amplitude of the wave vector k equals 2 pi over lambda, the wavelength of light. So this is like a very fundamental, often used equation. Please try your best to memorize this one, k equals 2 pi over lambda. It really helps out your journey during this course. So that's the amplitude of the wave vector. And many times you will be using it. And if you can remember it already from the beginning, it really helps a lot. Trust me on this one. Now, as I promised, this is a time harmonic wave. So the wave psi is also periodic with respect to time. And what this means, we just repeat the same kind of math we just did to discover what is the wavelength. So now we take the psi at the location of z equals 0, and now we log the time to be t equals 0. And now we are looking for a location in time where we have the first time the wave to be equal to the original wave. So at time equals tau, the equality holds, and this tau then corresponds to the period of the wave. So mathematically, this concept of period of the wave is exactly the same thing as the wavelength of light. So please see the symmetry in the mathematics. And now the period of the wave gives us a tools to understand what is the kind of oscillation speed of our wave. So what is the frequency of oscillation of our wave? And the frequency nu basically tells us how quickly the wave oscillates with respect to time. So nu is defined as the inverse of the period tau in this case, and in all the other cases also. In optics, instead of using the frequency nu, of course this depends on the field of optics, but especially on this course, instead of using nu or f as the frequency, we tend to use a more symmetric notation. So instead we mostly use the angular frequency omega, that is simply being just defined omega equals 2 pi over nu, and using this notion, using angular frequency, we can write the harmonic function, the harmonic wave, in a simple form that psi equals the amplitude of the wave a times the sine. And now inside the argument of the sine, we simply have k times z minus omega times t. And as you can now see, at least I really much more prefer this notation. This thing looks very symmetric. The phase term, the argument of the sine, so that this is the kind of reason why this has been chosen, this angular frequency to be used. So the phase term is now symmetric with respect to both z and t, and this at least helped me a lot when I was, and still it helps me a lot when I'm looking at a piece of mathematics. Easier to remember, easier to operate, I would say. And this is the choice we do, but of course there's nothing restricting you to also just use the common frequencies, nu or f. It's just a matter of taste. And now we are almost done for this lecture. I will just say a few words regarding the implications that arises from the wave nature of light. So now, when we would be, and we will be looking more into the propagation of light in the later parts of the course, and looking at the light-matter interactions, what we can see that the arises from this wave nature is that we start having interference phenomena. So basically, we can sum up waves. And some of the times the waves constructively interfere so that the waves get stronger in those locations or in those instances of time. And in other cases, there's destructive interference and the waves actually are being like vanishing or seem to be vanishing on those instances or in those locations. And we will also may have a phenomena of standing wave formation and so forth arising from the fact that we actually have waves that we are dealing with. Other phenomena that happens are diffraction effects, and of course interference and diffraction effects, they're very similar in nature, but mainly there's some subtlety in the kind of mathematics we're dealing with. But diffraction phenomena then kind of tells us also that what happens when the light is propagating and how we can do all sorts of things for light and what happens when light is propagating and interacting with matter. And when we are thinking of applications, and as an engineer, like I would say many times, we should think about applications. So it's really important to understand these basic principles. I admit that the course and our treatment is math heavy in a way, but still, this is really the basics that we must understand properly, that we could, for example, then understand how different instruments work. So for example, if you would want to understand more practical things like a resolution in optical microscope, or we would want to understand how in essence we would be detecting gravity waves, or how a spectrometer works, and how a diffraction grating works, we really need to understand the basic principles. We need to understand the basic pieces of mathematics that help us to understand what happens, and then based on that we can understand many things. And then we can also improve things in the applications. So this is my philosophy of things. We go math heavy a little bit because that provides us a kind of tools to then build on, like from that kind of basic knowledge. And now, like I promised, I will be saying a little bit about the different wavelength regimes. So of course, technically speaking, light as such, when we say light, it really strictly means of a electromagnetic radiation that has a very narrow or relatively narrow wavelength coverage. So when the wavelength of electromagnetic radiation is on the order of 390 nanometers and ranging all the way up to 780 nanometers, then we are speaking of light and not, for example, near infrared radiation or Röntgen rays and so forth. But this is actually the regime of light. So 390 corresponds to a color of violet, and 780 is a red. Already a 633 looks like red, so that this is actually very dark red, I would say, the 780. Our treatment is quite okay also at the ultraviolet wavelengths. So when we go to the shorter wavelengths than 390 nanometers, so especially in the nearby 200 to 400 nanometers, the treatment is perfectly okay. And the treatment is also quite okay at the near infrared regime and kind of mid infrared regime. So covering from 780 nanometers to all the way up to 6 microns. So even though technically speaking, this course is focusing on light, So at the wavelength regime or range of 390 nanometers ranging to 780, then of course we can slightly extend this beyond so that the treatment will be also fine in terms of UV wavelengths and the infrared regime. But many times when we would go beyond that, things start acting differently, so that you should be knowledgeable about this. For example, the kind of refractive index profiles of materials, they change quite dramatically. So when we would go to the UV wavelength regimes, and the same thing also applies when we go to the longer wavelengths. So the kind of behavior of materials, for example, changes, and then subsequently also the kind of what kind of light sources we can use and what kind of light sources exist. Those things change, so that you should be more knowledgeable if you would go into those regimes. But if you need to go there, of course, you can learn things on your own. So this is what I had to say on the first lecture. I thank you for listening me. And next lecture, I will be saying a few words about ray description of light. And needless to say, this will be more covered, the ray description, in our final chapter on geometrical optics. But nevertheless, like, it helps for us to kind of go through the things first quickly and then slowly start going through them again. So thanks for listening, and please stay tuned.